In this video, we're going to look at how to solve systems of linear equations using a technique called substitution, which implies we will be substituting something in or replacing or plugging something in. Now, there are 4 steps to this technique. I'm going to go ahead and organize them in sort of a circle, step 1, 2, 3, and 4. So we're going to be going in a circle here. The very first step, our job is to look at the 2 equations that we've been given and find one equation of the 2 where either a variable is already by itself or where it's really easy to get a variable by itself. So when I'm looking at these 2 equations, I notice that the bottom equation, y equals x minus 3, that y is already by itself. And it doesn't matter which letter, I just want a letter by itself. And so that's what I'll put in for my step 1. And then step 2, I'll use the other equation. So since I already used that bottom equation, step 2 will now use this other one, which is 3x minus 4y equals 10. So first steps begin with just writing down the original 2. Your first step shows an isolated variable. The second step shows whatever the other equation was. And this is where we now begin the substitution. What we're going to do is substitute this stuff into that. So this is telling me what y equals, and what that means is over here in this other equation where I have a variable y, I can now replace that symbol y with this value that y does equal, x minus 3. So this is the substitution step. Where there was a y, I replace it or substitute it with what I said y equaled, which was x minus 3. Now the reason this is helpful is because where in the beginning we had 2 different equations with 2 different letters, by substituting that y stuff in, now I have only one equation with just one variable. So now I can solve this using the same techniques I've used before to solve linear equations. So remember those steps. First, we want to distribute to remove parentheses. We want to simplify by combining like terms. We want to relocate letters to the left, numbers to the right, and then last we'll isolate. So for this example here, if I want to solve for x, the first thing I'll do is I will release it from parentheses using distribution here. So I have that 3x, and then negative 4 times x will give me negative 4x. Negative 4 times negative 3 will give me positive 12, and then I copy the equals 10. So there's my distribution, parentheses are gone. Now I combine like terms to clean up this left side. I notice there are 2 terms with x's. 3x minus 4x combines to give me negative x. Then I'll copy the rest. Next, I want to relocate. I want letters on the left and numbers on the right. It looks like my variable's already on the left side, so I do just need to relocate the number. I'll relocate this 12 by subtracting it. Remember, we relocate by adding or subtracting, and it's always the opposite sign of what we had. So because it was plus 12, I subtract 12. And so now I have negative x on the left. On the right, I have 10 minus 12, which is negative 2. So I have successfully moved the letters to the left, numbers to the right, and now my last step is to isolate that x. Technically, there is a negative 1 attached to it with multiplication, so I will detach that negative 1 using division. And so negative 1x divided by negative 1 is now x. On the other side, negative 2 divided by negative 1 is now positive 2. So I did find what x equaled. Now, if this was the equation from here, and I asked you to solve this equation, you'd be done. You have found what x equals. But this wasn't the original equation. The original was a system of equations. There were 2 equations and 2 variables to solve for. We have only found one of them. So as we're doing this in a circle, we want to come full circle here to work on our step 4. Where we figure out not only what this x equals, but now what does the y equal. So as we come full circle, I want you to look straight up to that original step 1. That original step 1 will help me find what y equals. It's utilizing x, which we just now solved for. We said that x was 2. So what we're going to do is we're going to rewrite this original equation, but where there was that original x, I will now say 2 because we know that's what x equals. And so y is going to be 2 minus 3, which is negative 1. And so we've now found an x value and a y value. And that's what we need for our solution. Remember that a system of linear equations, this is going to look visually in a graph like two lines, and they are going to intersect at a point. The point will be using these coordinates here. The solution is the point or the ordered pair x comma y, which in this case is 2 comma negative 1. So if I were to graph these two lines on a coordinate plane, I would find that they intersect at the point 2 comma negative 1. So again, with the substitution, you have these 4 steps. First step, you're using whichever equation I can use to get at a variable isolated very easily. Second equation uses whatever the other equation was. So let's try another example and get some extra practice. So here we have another example, which again, we want to solve by substitution. So our first step again, we want to pick one of the equations where one variable can be solved for easily or isolated easily. And in this example, it looks like the top equation is going to be the best one for us because x has already been isolated for us. So I'm going to copy that first equation for my first step. X has already been isolated. For the second step, I will use the other equation, which in this case is the 2x plus 3y equals 8. And now comes the substitution. This is where this technique gets its name. I want to take this expression that x represents and plug it in for, or substitute it in for, the variable x in this other equation. So where there was an x originally, and I now know that x is negative 2y plus 6, everywhere I see this x, I'm just going to put negative 2y plus 6. Because that's what x equals. So I have 2x, and then I'm going to copy the rest. I have to write plus 3y equals 8. Now again, here's where this substitution becomes helpful. Originally I had 2 different equations with 2 different letters in each. Now I have this one equation with just this one letter. Now I can work through that equation to find what the y equals. So again, our steps for solving a linear equation: first I want to distribute to get rid of the parentheses so that these terms are free and loose to move around. So 2 times negative 2y, this is our step 3 here. 2 times negative 2y will give us negative 4y. 2 times 6 will give us positive 12. And then I'm going to copy the rest. So there's our distribution. Now we need to combine like terms to clean things up. On this left side, I see that there are 2 terms that have a y. I have negative 4y plus 3y. So that's going to give me negative y. I'll copy the plus 12 and the equals 8. And so now to get y by itself, next thing I'm going to do is relocate the constant to the other side, move it out of the way. We want numbers on the right with our variable on the left. So we get negative y on the left. On the right we have 8 minus 12, which is negative 4. And last step, to isolate the y, we divide by the invisible negative 1 that was in front of it. Divide because it was attached by multiplication. So negative 1y divided by negative 1 is just y. Negative 4 divided by negative 1 is just 4. But that's not it. We have to come full circle here. So here comes step 4. And the reason I like organizing it this way is because when I reach that last step, I just need to refer to the original starting point. So I can just look straight up. And originally I had x equals negative 2y plus 6. Now where I used to have that y, I now know what y equals. Y equals 4. So I'm going to go ahead and substitute 4 in for y. And then I still have that plus 6. So I can compare these one on top of the other. Where there was a y, there's now a 4. So negative 2 times 4 is going to give me negative 8. And negative 8 plus 6 will give me negative 2. So I've now found an x value as well as a y value. That gives me the 2 coordinates that I need for my ordered pair, which is the point where these lines intersect. My solution will be negative 2 comma 4. Always put the x first in your first coordinate and the y in your second coordinate. Let's try some more. Okay, so remember for our first step, what we're looking for is which equation will either give us a variable that's already isolated or an equation where the variable can be easily isolated. So when I look at these two equations, unlike the previous two, neither of these are telling me x equals or y equals at the onset. So I have a little work that I'm going to have to do for this first step, but to make my job easier, I want to be careful about which equation I choose. Even though neither one already has something isolated, one of them will be easier than the other. So when I look at these two, it looks to me as though in the first equation, the y will be the easiest to isolate. The reason is because there's no number coefficient in front of y, so when I go to solve for it, I'll never have to divide by like a 3 or a 2, which means I won't have fractions. So what I would suggest in your step 1 is if you don't see an equation that literally says x equals or literally says y equals, find an equation that has a variable with no visible coefficient. So I'm going to take the first equation, because in that first equation, it's going to be easy for me to isolate the y without having to deal with fractions. And if I have choices that I can make, I want to make choices that are going to make things easier on me, not harder. So let's take this equation and try to get the y by itself. To get that y by itself, let's relocate the 3x, and since it's positive originally, let's subtract 3x from both sides. That leaves me with negative y on the left. And on the right, I'll have negative 3x plus 1. I'm not quite there. I still have a negative 1 attached to y. I need to detach it with division. But when I divide by negative 1, all I'm doing is I'm changing everyone's sign. I'm not actually dividing by a number that will create fractions. You can imagine if I had to divide by 2, 1/2 would create a fraction that I'd have to work with down the road. I don't want to work with fractions, so dividing by negative 1 is much easier. Negative y divided by negative 1 is just y. Negative 3x divided by negative 1 is positive 3x, and positive 1 divided by negative 1 is negative 1. So now I have this written in a nice y equals form, and it doesn't matter that it's y equals versus x equals, I just want a letter by itself, and so I've done that in step 1. Now step 2, I need to use the other equation. So for step 1, I used this top equation and manipulated it a little bit. Now in step 2, I want to use this other equation, so I'm going to use the 2x minus 3y equals 10. And in this second equation, or in this other equation, I take the expression that y was equal to and I substitute it in for that y. So where I saw the letter y, I am going to put what y equals. I'm going to put 3x minus 1. So I have 2x minus 3. Instead of the letter y, I will now have 3x minus 1. This is still equal to 10. And so again, the power of this substitution step is that I've gone from two different equations with two different letters. I've taken one and absorbed it into the other. So now it's one equation with just this one variable x that I need to solve for. So now we go to step 3, which is where we actually do the solving for that variable x. So first we need to distribute to release x from the parentheses. So I have 2x, and then negative 3 times 3x is negative 9x. Negative 3 times negative 1 is positive 3, and this equals 10. So now parentheses are gone. Now we need to combine like terms, so 2x and negative 9x combine to give me negative 7x. I still have the plus 3 equals 10. Now I'll relocate so that letters are on the left, numbers are on the right. So this 3 will relocate using subtraction. And now I have negative 7x equals 10 minus 3, which is 7. And then my last step of isolation, I want to divide by the coefficient negative 7. Luckily, this is not a fraction. I get x equals 7 divided by negative 7 is negative 1. I'm not done yet. I still have to come full circle here. Where I left off in step 1, I want to look straight up. Where I left off, I had an x there, but now I know what x equals. Let's plug that value in for x, and I'll learn what y equals. So y equals 3 times x, so in this case times -1 minus 1. So y equals 3 times -1 is -3, and then -3 minus 1 will give me -4. So I have found an x value and a y value. That's enough for my solution. Remember, the solution is the point where these lines intersect, and every point in two-dimensional space ought to have an x coordinate and a y coordinate. So our solution is the point -1, -4. Again, that's x, y. Let's take a look at another. So here again we have an example where we don't explicitly have an equation that says x equals or y equals, but there is an equation that is easier to manipulate than the other. So when I'm looking at these equations, I notice the second equation has an x that has no visible exponent. When there's no visible exponent, that's the giveaway, that's the easy guy to isolate. Everyone else has a coefficient in front of it. Those will create fractions, and if I can avoid fractions, I'm going to. I'm going to choose this x that has no visible exponent to be the guy I isolate in step 1. So for step 1, let's utilize this bottom equation, x minus 2y equals -11. And we want to isolate the x, again, because it has no visible exponent. That's the right choice. So let's relocate the y to the other side. Since it's negative, let's add 2y to both sides. That'll relocate it. And so now on the left, I have x. On the right, I have the 2y and also that -11. And it looks like that's all I needed to get a letter by itself. And that's the goal of the first step, is to choose one equation and get one letter by itself. And there are other choices we could make, but I'll tell you right now, if you tried any other equation or any other letter, you would wind up with fractions. So if you can avoid the fractions and be wise in who you choose, I would recommend that. So now for the second step, we're going to use the other equation. So since this was the bottom equation, step 2 will take the top equation. So -5x plus 3y equals 6. And what I want to do is I want to absorb this information into the other. So take this equation and put that information into this other one. This equation told me what x equaled. And so that means the x in this other equation can be written in a different way. Instead of saying the symbol x, I can replace that symbol with the expression 2y minus 11. Because x does equal 2y minus 11. Everything else will stay the same. So after the x came plus 3y equals 6. Again, the power behind this substitution step is that instead of 2 equations with 2 letters to solve for, we now have one equation with just this one variable y. So now we move to step 3. Step 3 is where we want to now solve for that one variable y. First thing we need to do is release y from the parentheses, so we will distribute. -5 times 2y gives us -10y. -5 times -11 gives us positive 55. And then I'll copy the rest. Now I want to clean up the left-hand side by combining like terms. So I have -10y plus 3y. That's going to give me -7y plus 55 equals 6. Again, I'm trying to get the y by itself. Let's relocate the constant to the other side. Since it's added, let's now subtract 55 from both sides. Then we're having -7y on the left. And then on the right, 6 minus 55 is going to give us -49. Last step is to isolate y using division. Since that -7 is attached with multiplication, we detach it with division. And so now we have y on the left, and then on the right, -49 divided by -7 is a positive 7. So we figured out what y equals, but again, we have to come full circle to our step 4 here, last step. And in this last step, we look straight up to where we left off. And in this last step, where we left off in step 1. We had a y symbol there, which now that we know what y equals, we can substitute that value in. So we've got x equals 2 times y, and again, instead of y, I will put 7 because that's what y equals, and then minus 11. So again, when you compare where you left off in step 1 with where you begin in step 4, they look identical, except where there was this letter, there's now this number we had solved for. So now cleaning it up, x equals 2 times 7 is 14. 14 minus 11 will give us 3. And so we have our x coordinate and our y coordinate. And so we'll write our solution as an ordered pair because, again, we want to emphasize that the solution to a system is the point where these two lines are intersecting. So x is 3. Y is 7. Sometimes you find x first and then y, sometimes y first and then x. Always make sure when you write your solution that x is the first coordinate and y is the second. Let's take a look at a few others that might get a little bit harder. Again, for our first step, we want to find an equation that either isolates a variable or makes it easily isolatable. So, and I look at these two equations, the key for determining where the easy isolation is which of these variable terms has no coefficient in front of it that you can see, and in this case it's from our top equation, it's the y. So for step 1, I'm going to use this first equation, 10x plus y equals -5, and because y has no visible exponent, he's the guy I want to isolate. So let's relocate the 10x. Since it was positive, let's subtract to remove it, and we'll do that on both sides to maintain the balance. And we wind up with y equals -10x minus 5. So we've isolated a variable. That's what we want to do in step 1, get a letter by itself. And then step 2, we need to use the other equation. So we've already used the top equation. Step 2 will utilize the bottom equation. So -5x plus 2y equals 10. And this is where the substitution happens. So where there was a y in this equation, we're going to plug in this new expression, -10x minus 5. So I'm copying everything, but where I saw originally this letter y, I'm going to replace it with what y equals, which was -10x minus 5. Everything else about this equation should match the same. So everything's the same except where there was a y, there's now -10x minus 5. And again, what this has done is it's absorbed the two equations together, and now I have one equation with just one letter. So for step 3, my job is now to solve for this one variable x. I begin by releasing it from the parentheses using distribution. So I've got -5x. And then 2 times -10x will give me -20x. 2 times -5 will give me -10. And then this equals 10. So now that the parentheses are gone, I want to clean things up a little bit by combining like terms. -5x minus 20x will give me -25x. Now I want to relocate so that letters are on the left, numbers are on the right. I've already got my letter here, so I want to relocate the 10. I'm going to add 10 to both sides because it was originally negative. Add 10 to both sides. So now I've got -25x on the left. I've got 10 plus 10, which is 20. On the right, so letters are on the left, numbers are on the right. My last step is to isolate. I want to divide by this coefficient, -25. And this is where things get more interesting because 20 divided by -25 is not a nice whole number like we've seen so far. We are going to have a fraction. It is going to be negative, positive divided by negative, but we need to make sure that the fraction is simplified. So when you're looking at the fraction and trying to simplify it, ask yourself, is there a greatest common factor that goes into 20 and 25, that goes into the top and the bottom? In this case, I see 5 goes into 20 4 times, and 5 goes into 25 5 times. That's going to help me reduce this fraction. So -25x divided by -25 is x. A positive 20 divided by a negative 25 will be a negative fraction. It reduces to 4 over 5. Now, if I were graphing this, looking for an intersection point, you can imagine trying to find negative 4/5 on a graph. That's going to be a lot harder. You're not going to necessarily guess negative 4/5. Maybe it would have looked like negative 3/4 or negative 0.9 or something like that. You wouldn't necessarily know that it was exactly this. So this substitution technique is very nice when you don't have perfect whole numbers. But we're not done yet. We do have to come full circle, taking our step 4. We begin by looking at where we left off in step 1 and picking up from there where we had the letter x before. We now replace it with this new number that we know x equals. We're going to replace it with negative 4/5. And then we subtract 5. Now, when you're mixing whole numbers with fractions, the arithmetic can get a little bit trickier. I would suggest, if you're going to go off to the side to do this, I would suggest that you write the negative 10 as a fraction, negative 10 over 1. You're going to multiply it by a negative 4 over 5. So negative 10 times negative 4/5, we're going to write it as negative 10 over 1 times negative 4/5. Negative times negative is going to be positive. And we multiply fractions straight across. Up top, 10 times 4 is going to give me 40. On bottom, 1 times 5 is going to give me 5. Again, negative times negative is positive. And now 40 divided by 5 gives me a perfect 8. So even though I had a fraction for x, it turns out that I'm going to have a whole number here. So negative 10 times negative 4/5 we said was positive 8. 8 minus 5 will give us 3. So this is an example where graphing would have not necessarily given us the exact perfect solution. Visually, when we're looking at fractional amounts, we can't necessarily guess the perfect exact fraction right off the bat. So this is a nice algebraic technique for getting the exact precise answer rather than trying to eyeball it and guess. So here our solution, again, we want to write it as an ordered pair to signify this is a point where these lines are intersecting. We always begin with the x value, in this case negative 4/5, and then the y value, which is 3. Let's try another one with fractions and see how we do. Again, as we begin step 1, we're looking for an equation that either says x equals or y equals. And I don't have that here, so the next best thing is if I can find an equation where it's easy to get x equals or y equals. And the way to tell if it's easy is if you can find a variable with no visible coefficient attached to it. So in this case, the second equation, the x is going to be the one we want to isolate. Everyone else has a visible coefficient. Those will result in fractions, and if we can try to avoid fractions, we want to. So let's try that second equation, negative x plus 6y equals 0, and we want to get the x by itself, so it says x equals. So first I'll relocate the 6y to the other side. Since it's a positive 6y, I'm subtracting to relocate it. That leaves me with negative x on the left, and 0 minus 6y, the 0 doesn't contribute anything, so it's just going to be negative 6y. And then last but not least, I want to isolate the x by dividing by the negative 1 that's in front of it. And I do that to both sides, and all that does is when I divide by a negative, it changes everyone's sign. So negative x turns into positive x. Negative 6y turns into positive 6y. And so now I have an x equals, and I'm going to take now my second step, beginning with the other equation. So this x equals 6y, that came from the bottom equation. That was the equation we used in step 1. So now in step 2, I'm going to use the top equation, which we haven't used yet. 2x minus 9y equals negative 2. And what I'll do is I'll take this value for x and absorb it into this equation. So since I know what x equals, where I saw the letter x, let's replace it with what x equals. So x equals 6y. Instead of the letter x, let's use 6y instead. And copy everything else. So I'll copy minus 9y equals negative 2. Okay, so now I have one equation with just one letter to solve for. I'm going to go ahead and multiply. It's not really distribution because there's no addition or subtraction happening in here, but 2 times 6y gives me 12y. Then I have minus 9y equals negative 2. This is my third step. I'm starting here by trying to solve for the y. 12y minus 9y gives me 3y. And if I try to isolate that y by dividing by 3, I wind up with y equals negative 2/3. Now, it's a fraction. That's okay, we'll deal with it. I just want to make sure that that fraction is simplified. So when I check for whether a fraction is simplified, I'm looking at the top and bottom and asking if there's a greatest common factor that they share. And so here the only factor that goes into 2 and 3 is 1. If it's mutually prime, if the GCF is 1, that's how I know it's simplified. So that's going to be my value for y. But now I need to come full circle and find what the x equals. Whoops, that's step 4. I need to come full circle and find what does the x equal. So if I look straight up, it told me that x was going to equal 6 times whatever the y value is. X is 6 times y. Well, if I know that y is negative 2/3, then I can just go ahead and plug that in. So to find what x equals, all I have to do at this point is multiply 6 times negative 2/3. But again, when I mix the whole numbers and the fractions, it gets a little bit tricky, so let's go off to the side. I'm going to rewrite 6 as 6 over 1, make it look like a fraction, and I'm multiplying by negative 2/3. Now when I multiply a positive times a negative, I know my answer will be negative. I'm going to multiply the fractions straight across, so upstairs 6 times 2 is going to give me 12. Downstairs 1 times 3 is going to give me 3. And negative 12/3 is the same as negative 4. So this turned out to give me a whole number for x, which is nice. We get negative 4, and now that I have a value for x and a value for y, I can write my solution as an ordered pair. X is negative 4, y is negative 2/3. So this is just another example where if you had tried to graph these equations in order to solve, in order to find the point of intersection, the intersection point would not be composed of nice, perfect whole numbers. There would be fractions involved, and when you're dealing with fractions in a graph, it's very difficult to make a good guess as to what the exact precise fraction is. Again, that's where the algebra technique versus the visual graph technique, the algebra becomes a lot more precise and a lot more helpful. So I have 2 more examples I want to show you, and they both are the special cases. We saw when we were graphing that it's possible that the lines are parallel, and that represented an inconsistent system where there was no solution. We also saw that there was a possibility where the lines were the same, and so they intersected everywhere on the line. We called that a dependent system, and there were infinitely many solutions. Let's take a look at how that visualizes, or how that appears in the algebra versus the graph itself. So as always, we take our first step where we're trying to isolate one of the letters. If an equation gives us explicitly x equals or y equals, we'll take it. In this case, we don't have that, so we're going for the next best thing, which is, can I find a variable that can be isolated easily and without fractions? The giveaway is if I can find a letter that has no number in front of it that I can see. These other variables show coefficients in front. Those will result in fractions down the road. Let's not do that. Let's try and get this y isolated. So for step 1, I'm going to utilize that second equation, negative 2x minus y equals 4, and I'm going to try and get that y totally by itself. First, I'll relocate the x to the other side. Since it's negative, I will add. And so now I have negative y on the left. On the right, I have 2x plus 4. To get the y totally isolated, I divide by the negative 1 coefficient that's technically in front of it. And again, negative 1 is not going to change any of the numbers, it's just going to make all the signs different. So negative y turns to positive y, positive 2x turns to negative 2x, and positive 4 turns to -4. So again, what I've done is I've chosen an equation and isolated one of the letters. It doesn't have to be a y, it doesn't always have to be one equation or the other. I would just recommend trying to find somebody who has no visible coefficient, because it means that when he's isolated, there are no fractions that you're going to have to deal with. So now step 2, we have to use the other equation. Since I already used the bottom equation, now I'm going to use the top equation. So I need 4x plus 2y equals 5. And what I want to do is I want to absorb this into the second equation. So where I see the letter y, since I now know what y equals, where I see the letter y, let's substitute that symbol with this expression here. So I'll have 4x plus 2 times, instead of y, I will use -2x minus 4, because that is what y equals. And this is now equal to 5. So these match, except where there was a y, there's now -2x minus 4. And so that's the substitution. And again, where it's powerful is it's created now just this one equation with this one letter that I need to solve for. So for step 3, let's try to solve for x. Right now it's trapped in parentheses, so I will distribute to remove those parentheses. I've got 4x, and then 2 times -2x is -4x. 2 times -4 is -8, and this equals 5. So now, if I combine like terms here, the x's go away. They cancel out completely, and I wind up with -8 equals 5. And if I told you that -8 is the same as 5, you would tell me, no, that's not true, you're wrong, that's false. This is a false statement. It doesn't tell me anything about x. X has completely dropped away. If this is a false statement, in math, a false statement is described as a contradiction. And if I had just a linear equation that led to a false statement or a contradiction, I would say that there must be no solution then, because the whole point is to solve for x, find what x needs to be to make this true. But if x goes away, that means x doesn't matter. No matter what x is, I will wind up with something that's not true. So there is no solution to this system. And so actually these funky examples where we have either no solution or infinitely many, they're actually easier, because what happens is I hit a dead end. If I can't find x, I can't plug it in to find y either. So I hit a dead end at this point. I have no solution. And so let's remember what that means as far as the graph is concerned. If I actually graphed these two linear equations, I would have two lines that were parallel to each other. They're parallel, meaning they will never intersect. And so there's no point of intersection. That means there's no solution. So when I get no solution, it's because I have hit a dead end, x has gone away, and I'm left with a false statement, a contradiction. This is no solution. It would look like parallel lines, and this is what we call an inconsistent system. So let's take a look at just one more, where instead of no solution, we get infinitely many. Again, as I begin step 1, I'm looking for an equation that helps me get x equals or y equals. If it's not already going to explicitly say that, then I'm searching for the variable that has no visible coefficient. In this case, it's the x from the top equation. So for my first step, let's choose that top equation, x minus 3y equals 6. And my job is to isolate that x to get it by itself. So I will relocate the 3y by adding to both sides. This then gives me x equals, which is exactly the format I want. I get 3y plus 6. So there's my step 1, and step 2 will need to use the other equation. So this came from the top equation. I now need to use the bottom equation, which is negative 2x plus 6y equals negative 12. Again, in this second step, this is where the substitution happens. So this is where I take whatever x equals and I throw that in for x. So since I found what x equals here, I'm replacing x with that statement. So I'll have negative 2, and then instead of x, I will see 3y plus 6. and the rest of this stays the same. So I'll still see the plus 6y equals negative 12. So now I've got one equation with just this one letter to solve for. Here comes step 3. I want to find what y equals. And so first I need to release y from the parentheses. I'll use distribution here. And negative 2 times 3y is going to give me negative 6y. Negative 2 times positive 6 is negative 12. And plus 6y equals negative 12 can get copied. So I've released the y from parentheses. Now I need to combine like terms, but negative 6y plus 6y cancel each other out. So I wind up with just that negative 12 on the left, set equal to the negative 12 on the right. Now if I told you that negative 12 was the same thing as negative 12, you would agree. It's exactly the same thing. This is a true statement. And the fancy math word we use to say true statement is we call this an identity. An equation that's always true is an identity. So what does that mean? Well, when we were looking at plane equations, we would have said, okay, so all real numbers will work. If the y is dropping out, it means y doesn't matter. No matter what y is, we'll always have truth. And if that's the point of solving an equation, is to find the truth, we'll always have it. No matter what y is, y could be any real number. Well, rather than saying any real number, remember we're thinking about a point of intersection, a point in two-dimensional space. Where are these lines intersecting? Well, they're not going to intersect absolutely everywhere, because then it wouldn't be a line, it would be a full plane. So let's maybe consider how we would say this. If we have truth all the time, then every y is a solution. This is going to end up being infinitely many solutions. Let's see if we can remember what the picture looks like if there's infinitely many. So normally lines intersect at a point. We saw in the last example, if we had parallel lines, it was no solution. If it's infinitely many, it means that they're not just parallel, they're actually the same line, and they intersect everywhere on that line itself. So this is an example of lines that are the same line. It's infinitely many solutions, but I just want to be careful to say it doesn't mean everything's a solution. So for example, if I had graphed these lines, and let's just say that the lines looked like this, and then they overlapped on each other, where are the solutions? The solutions are everywhere on that line. That's not a solution. That's not a solution. These are not on the line, and so those are points not on the line. Those are not solutions. So there are infinitely many solutions on the line, but there are also infinitely many points that are not solutions because they're not on the line. So just be careful about saying everything is a solution, because not everything is. It's just everything on that line is a solution, and there are infinitely many points there. So just be careful as you're going through the homework. Again, you should see some drop menus where they're asking, is this a inconsistent system with no solution? Is it a dependent solution or a dependent system with infinitely many solutions? Or in most cases, it'll just be, these are your typical run-of-the-mill two lines that cross, where's that intersection point? But in all these cases with substitution, you're doing the 4 steps. Sometimes you hit a roadblock and you stop prematurely because it's a special case, but most of the time you get through 4 steps and you'll find the 2 coordinates for your 1 point of intersection between the lines.